Okay, so what I'm going to try to do here, because the audio got screwed up, is I'm going to play the film for y'all and talk through it um, the best I can. It might be a little choppy, but at least then you'll have some explanation. So here we go. So we've got a system with two batteries, one 9-volt, one 6-volt. You can see that the batteries are hooked up so that the positive terminals are hooked up so that it's positive to positive. So the current's being pushed from the 6-volt battery in this direction and from the 9-volt battery in this direction. So the first thing we have to do, and that's what I'm drawing right now on the video, is to find current direction, because what we're going to try to find is current and voltage that the current through each of these resistors and the voltage drop across each. And then we're also going to make a graph for the change in voltage versus, this is an S for displacement, as we start at this negative terminal here and work our way around the loop. And so that's what I'm going to start working on here in just a minute. So one of the things that I should note is that when you define current, the direction doesn't matter as long as you're consistent about that direction at the end. And if it turns out you get a negative answer, well, that just means that the current goes in the opposite direction than which you said it would at the beginning. But the direction doesn't matter. It only matters that you're consistent. So here we go. So the net change in voltage around this whole loop has to be zero. This is one of Kirchhoff's laws. This is known as the loop law. So as we travel from here around the loop back to here again, our change in voltage has to be zero. So what I've done in this equation here is just lay out the different elements of the circuit. So first we have VB1, then we have VR1, so that's R1, then we have VB2, the 9-volt, and then we have VR2. And as we go across both of those, or across all of these elements, the net voltage is going to be zero. All right, so just a bit of nomenclature. This E here means EMF, which is a classical idea about electricity known as electromotive force. All right, now Ohm's law says V or E, epsilon, equals current times resistance. So if I'm subbing the change in voltage for the resistor 1 here, I can just say IR. And whenever you cross a resistor, your voltage drops. So we have the voltage gain from the battery, 6 volts, minus the initial voltage lost at the resistor 1, minus IR1, minus E2, and in this case it's minus E2 because I hooked up this battery backwards. Normally, so if this was hooked up, so this was the negative terminal and this is the positive terminal, it'd be plus E2. And then we have minus IR2 here, and that all equals 0. All right, and then I'm just doing a little math. I'm factoring out, so I've moved the two E's here, so E1 minus E2, and then I've subtracted from that the current, because these two I's have to be the same. In any loop, any continuous loop, the current is going to be the same. So in this situation, since there's no branch or anything like that off of it, the current's the same to the whole thing. So I can factor this like that, set it equal to 0, do a little more math, and solve. So like I said earlier, since I got negative 0.5 amps, it means I assigned it in the wrong direction. And this makes perfect sense. If we think about batteries in terms of their strength, the 9-volt is stronger than the 6-volt. And so the current is going to go this way. And so by setting it in the wrong direction, not a big deal, just means that it's in the wrong direction. I have the right magnitude here though. So now, using this current, I can determine the drop in voltage across each of the elements. And so that's what I'm doing here, which is to find the change in the potential across this first resistor, the 4 ohm resistor. You just take the current, which is 0.5 amps, or negative 0.5 amps, and you multiply it by the resistance, which is negative 2 volts. Now, just a quick note on negatives and positives here. I misspoke there. The reason here that this is negative 2 volts is because whenever you go across a resistor, your potential drops. Now, I've reset the current in this direction. If we were being absolutely consistent, this should actually be a gain across this. And then this one should also be a gain. But that's just to be consistent with the negatives. So now I'm graphing it. We're looking at voltage versus displacement. So you can see first we gain 2 volts across, or 6 volts, excuse me, across that first battery. Then we're in the top wire, so we have no gain, no loss because it's an ideal wire. Then we drop 2 volts as we cross that first resistor. But since it's backwards, we actually gain 2 volts. There it is. I was writing very slowly. I must have had a lot more to say the last time we did this. All right, and then we go through an ideal wire again. And then, since our battery's hooked up backwards, we're going to lose potential here instead of gain it like we normally do with batteries. But again, this is just directional. So now we're down to negative 1 volt because we went up to 8 and we dropped 9, so we're at negative 1 volt, which means that resistor, and the math works out, is going to bring us back up 1 volt, back to 0. So that's our total displacement. All right, so that's a 2-battery circuit where the batteries are hooked up in series, but so that the positive terminals are hooked up for the positive terminals. And this is why when you hook up a couple of batteries backwards in some kind of appliance, they often don't work because the batteries have almost the same voltage. So the voltages just cancel out.